자, 우리가 이런 형태의 연속보를 이제 설계합니다. 슬라브는 연속보니까요. 그런데 이 모멘트가 아래 위로 이동하는 그 스팬은 양쪽 끝에만 그렇다고 이제 고려하고요. 가운데는 똑같은 모멘트 다이어그램을 갖는다, 이렇게 보는 겁니다. 즉, 이 내부에 있는 스팬들은 서로가 강하게 고정되어 있다, 이렇게 보는 거죠. 서로가 강하게 고정이 되어 있다, 이렇게 보는 겁니다. 단 외부 스팬, exterior 스팬의 경우에만 단부의 영향을 받는다, 이렇게 보는 거죠. 그렇죠? 이해가시죠? 그래서 중앙부 모멘트는 단부 모멘트의 형태를 갖고, 즉 완전 고정단 단부 모멘트, 그리고 고정이다. 그래서 이 단부 모멘트라는 표현은 고정단, 이렇게 한번 추가를 해볼까요? 고정단부 모멘트 형태를 갖고 완전 고정이다. 그 이유는 이제 외부 영향을 받지 않는다, 이런 뜻이죠. 요 가운데는 여기서부터 여기서부터 요 맨 외부에 하나 앞에까지, 그렇죠? 이해가시죠? 그리고 요 외부만 영향을 받는다. 그래서 외부가 만약에 핀 접합이면은요, 이렇게 0으로 시작되겠죠. 그래서 이제 얘가 원래는 이 완전 고정단일 때 요거 기준으로 이게 맨 아래에 존재한다 그랬죠. 요 아래 이상은 더 못 내려간다 그랬어요. 그죠? 요 아래 이상은 못 내려갑니다. 그러니 여기서 이제 완전 핀일 때는요, 핀일 때는 올라가죠. 그죠? 올라가고, 또 핀에서 어느 정도 고정이 되어 있으면 또 좀 내려가겠죠. 그죠? 그래서 여기서 이 모멘트, 부모멘트죠, 여기가. 우리가 이거를 부모멘트라고 합니다. 부모멘트. 그래서 제가 모멘트 다이어그램을 이렇게 그리는 이유가 부모멘트를 마이너스 쪽에 표현하는 거죠. 근데 또 많은 책들을 보면은 이렇게 그리죠. 이렇게, 그죠? 이렇게 그리고 여기를 부모멘트 이렇게 읽어요. 부모멘트. 뭐 정신만 바짝 차리면 괜찮은데요. 나중에 이제 밴딩 모멘트 다이어그램이 복잡해지면 막 부정 이게 헷갈립니다. 그래서 저는 아예 처음부터 이렇게 방향을 딱 잡아서 그리는 거죠. 그래서 이제 요 사이를 왔다 갔다 하는데 이게 핀이 돼가지고 단순보가 돼가지고 모멘트가 0이 될 때는요, 얘가 올라가서 이렇게 많이 축 좀 빠지는 이런 형태를 갖게 되겠습니다. 그리고 중간쯤 어디면은 이렇게 되겠죠. 그렇죠. 그래서 이 담보 조건에 따라서 여기 M0에 대한 퍼센테지가 바뀌겠죠. 여기가 얼마라 그랬죠? 그러니까 여기가 0.65 M0였죠. 0.65. 여기도 0.65. 다 0.65죠. 여기는 0.35였죠. 기억나시죠? 네. 그리고 이제 이것도 변하겠죠. 그리고 이 안에는 안 변한다는 얘기죠. 그래서 여기를 보시면요, 이제 담부 조건이 완전 고정도 아니고 완전 단순도 아닌 어중간한 고정단을 가졌을 때는요, 0.65에서 이제 위쪽으로 이동을 한다 그랬죠. 위쪽으로. 기억나시죠? 위쪽으로 이동을 한다 그랬습니다. 그래서 여기 있던 0.65에서 위쪽으로 이동을 하면서 이게 좀 내려가죠. 그죠? 이렇게. 그래서 여기 조금 격차가 있는 겁니다. 여기에. 그리고 이제 이 내부 쪽은 무조건 다 고정단이다 그랬어요. 그죠? 고정단이다. 이 내부 스팬은요. 여기는 이제 우리가 엑스테리어 스팬이라고 부르고요. 여기는 이제 인테리어 스팬 이렇게 부릅니다. 저희는 항상 이거로 나옵니다. 그죠? 자, 그래서 이제 우리가 도표를 보면요. 이제 도표가 좀 이해가 가시죠? 그죠? 요 도표는 지난 시간에 공부한 거죠. 엑스테리어 스팬에 대해서만 그린 겁니다. 그러면 인테리어 스팬은 왜 안 그려줍니까? 그죠? 인테리어 스팬은 그릴 필요가 없죠. 왜냐하면은 무조건 0.35하고 0.65니까. 그렇죠? 설명드린 대로. 엑스테리어 스팬만 그린 거다. 그런 거세요. 그래서 완전 고정일 때는요. fully restrained일 때는 우리가 배운 대로 0.65, 0.35. 그죠? 이 얘기는 뭐냐면은 아까 보신 대로 완전 고정일 때는 0.65, 0.35, 0.65, 0.35 이 패턴이 반복이 되는 거죠. 그런데 얘가 조금 이제 단순보 쪽으로 흘러가면요. 여기는 작아지고, 그렇죠? 여기는 커지고, 여기도 좀 커지고, 그렇죠? 그렇게 되겠죠? 그래서 보면요. 완전 이제 단순보로 풀릴 때요. 그죠? The exterior edge unrestrained 됐을 때는 여기 0이 되겠죠. 무조건 0이죠. 그 다음에 여기가 이제 0.63으로 올라갔죠. 0.75. 이렇게 되는 거죠. 여기가 0으로 됐죠. 여기 0.65에서 0이 되어버렸죠. 단순 보니까 모멘트가 이제 안 걸리니까요. 그다음 0.35짜리가 올라가서 0.63이 됐죠. 올라가겠죠. 이렇게. 그러면 쭉 빠져가지고 여기가 이제 0.75가 되는 겁니다. 이렇게 모멘트 다이어그램이 이렇게 되어 있는 상태에서 이렇게 변하는 거죠. 그래서 요거는 이제 이쪽하고 단부 조건이 다르니까 0.65 이하로 내려갈 수가 있는 거죠. 단부 조건이 다르기 때문에. 자, 어쨌든 간에 0, 0.63, 0.75 이렇게 되어 있는 거죠. 이해가시죠? 요 단부 모멘트의 변화. 이거를 구조 해석을 일일이 할 필요가 없이 이 표를 우리가 읽게 되면은 쉽게 구조 해석을 이제 도표로 푸는 거죠. 자, 그래서 이렇게 이제 각각의 조건들이 이제 3개가 더 붙었어요. 이게 양극단이 되겠죠? 완전 고정. 그 다음에 exterior edge unrestrained, exterior edge fully restrained. 자, 두 번째 경우에는 이제 이 경우죠. Slab with beams between all supports. 그러니까 모든 서포트에는 빔이 있는 그런 슬라브예요. 이런 슬라브가 되겠죠. 모든 서포트에는 이렇게 빔이 있어요. 그죠? 모든 슬라브에는 빔이 있는 그런 슬라브가 되는 거죠. 두 번째 경우죠. 그리고 이제 세 번째, 네 번째 경우는 이제 slab without beams between interior supports. 얘는 이제 서포트에는 전체적으로 빔은 없어요. 없지만은 맨 끝단에는 이제 빔이 있을 수 있고 없을 수 있다. 우리가 맨 끝단에 있는 빔을 엣지 빔 이렇게 얘기를 하죠. 그래서 세 번째, 네 번째는 여기죠. 어쨌든 간에 이 서포트에 빔이 하나도 없어요. 이렇게. 그런데 끝단에만 있을 수 있고 없을 수 있고 엣지 빔. 그렇죠? 그래서 이렇게 우리가 5가지가 있죠. 완전히 단순 뭐 빔. 그다음에 여기 하나가 이제 완전 고정이 하나가 있죠. 5번째. 그죠? 그래서 우리가 양단 고정도의 강한 정도로 볼 때는 이제 완전 고정이 제일 강할 것이고요. 그 다음에 이제 요게 강할 것 같고, 그 다음에 요거, 그 다음에 이제 이거랑 비슷하고, 이렇게 되죠. 그래서 여기 보면요. 여기 보면은 이제 이 exterior negative factor들이라고 그랬죠. 아까 exterior negative factor. 그게 뭐였죠? 여기였죠. exterior negative factor. 그렇죠? 그래서 여기 가서 보면요. 여기 가서 보면은 여기는 이제 0이 되겠죠. 그 다음에 있는 거. 오케이. 그래서 요 표를 보면요. 요 표를 보면은 우리가 얼마나 강력하게 고정이 되어 있는가를 이제 간접적으로 알 수가 있죠. 그래서 완전 고정일 때가 제일 깊숙하게 내려가고요. 그다음에 단순 보일 때는 이제 0에 걸쳐 있겠죠. 그리고 이제 조건에 따라서 조금씩 내려가는 거죠. 이 표 읽기 쉽죠? 그리고 미드스팬도 마찬가지죠. 강력하게 고정이 되어 있는 경우가 이번에는 이제 반대로 제일 작겠죠. 왜냐면 얘는 이제 많이 올라가야 되니까 서서히 내려오죠. 이렇게. 그죠? 그 다음에 이제 인테리어, 네거티브 인테리어. 이게 이제 익스테리어 스팬을 얘기하는 거예요. 인테리어라는 게 혼동하시면 안 됩니다. 인테리어라는 거는 여기 엑스테리어 스팬에서 인테리어 여기를 얘기하는 거예요. 여기가 아니고 엑스테리어 스팬에서 인테리어 여기 얘기하는 거예요. 그래서 엑스테리어 스팬에서 엑스테리어 매드 인테리어. 아시겠죠? 몇 번 말씀드렸어요. 그래서 이 표는 단순히 엑스테리어 스팬에 관련된 표고 인테리어 스팬에 대해서는 표가 없다. 왜? 전부 다 이거기 때문에 이런 말씀을 드렸습니다. 그래서 이제 이 경우가 완전 고정될 때가 여기 있었고요. 미드 인테리어. 그다음에 이제 여기 있는 경우가 여기죠. 그죠? 그다음 여기 있는 경우가 여기 있는 경우가 여기 이렇게 해서 우리가 이 표를 보면은 잘 이해가 안 가죠. 무슨 말인지. 그죠? 이 표를 좀 자세하게 해설을 하면 이렇게 되는 겁니다. 이해가시죠? 이렇게 되는 겁니다. 그랬을 때 우리가 이제 구조 해석을 거치지 않고 모멘트 다이어그램을 우리가 이렇게 그릴 수 있다. 그래서 여기 보면은 이제 인테리어는 무조건 다 고정단 모멘트를 따른다. 엑스테리어에만 우리가 단부 조건에 따라서 상하를 오르락 내리락 한다. 오르락 내리락 할 때의 요 개수, 여기 개수, 그죠? exterior, mid, exterior, interior. 그렇죠? 자, 지금 많이 반복하고 이제 나중에 문제 풀 때는요, 반복을 하지 않습니다. 계속 뭐 반복할 수 없잖아요. 같은 얘기를, 그렇죠? 그래서 여기 보시면은요, 이제 이런 개수를 가지고 오르락 내리락 하는데 여기서 이쪽으로 갈수록 고정단의 고정도가 강해진다. 이렇게 보시면은 맞습니다. 그래서 굉장히 잘 만들어진 표죠. 이렇게 이거를 잘 이해를 하시기 바랍니다. 그리고 여기에 우리가 이제 표를 보고 숫자를 픽업을 합니다. 그래서 이 중간에 있는 그런 경우는 이제 슬라브에서는 없습니다. 요 다이렉트 디자인 메소드에는 없습니다. 걱정하지 않으셔도 되겠습니다. 자, 이제 다 이해가셨죠? 자, 여기도 마찬가지죠. 이건 좀 자세하게 들여다본 거죠. 그죠? 그래서 완전 고정일 때부터 쭉 올라가겠죠. 이렇게, 그죠? 여기도 마찬가지고요. 이거는 이제 우리나라 코드에 있는 내용을 우리나라 말로 정리하는 표입니다. 이렇게요. 그래서 여기 있는 미국 ACI 표하고 뭐 똑같죠? 예, 똑같습니다. 왜냐면 구조 해석은 뭐 다를 게 없지요. 미국이나 우리나라나. 이렇게 해서 구속되지 않은 외단, 모든 받침부 사이에 보가 있는 슬래브. 번역을 하는 거죠. 내부 받침부 사이에 보가 없는 슬래브인데 엣지빔이죠. 테두리 보가 없는 경우, 있는 경우. 완전 구속된 외단. 여기는 이제 전부 다 이 모멘트는 이제 여기에 관련된 해설이죠. 외부. 이걸 잊으면 안 되겠습니다. 그래서 이제 정리를 한번 해볼까요? 여기 보시면은 모멘트가 이제 0이죠. 1번 경우에는 얘는 점점 내려가겠죠. 단부가 고정도가 심화될수록 얘는 점점 내려가죠. 여기서는 여기서는 일로 올라가는 거죠. 그러니까 얘는 내려가고요. 오케이. 그래서 얘는 내려가고 얘도 여기서 높이 올라가서 좀씩 내려가고, 그죠? 다 그런 거죠. 그 철근을 보면은 이 경우에는 우리가 부 모멘트에는 이제 탑바가 지나간다. 이렇게 배웠죠? RC1에서. 그래서 부 모멘트라고 하면요. 이제 상부에 인장이 생기는 거를 얘기를 하거든요. 그쵸? 부 모멘트의 정의가 뭐죠? 구조 해석에서 부 모멘트는 상부에서 인장이 생긴다 그랬어요. 그죠? 그래서 상부에다가 철근을 이렇게 보강을 해줘야 되는 거죠. 여기는 이제 부호 모멘트가 두 군데가 되겠죠. 같이. 이렇게. 여기는 이제 정 모멘트는 따라서 뭡니까? 하부 인장이죠. 하부 인장. 여기다 해주는 거죠. 하부 쪽에. 부 모멘트 존이, 여기가 정 모멘트 존이죠. 여기가 부 모멘트 존이고, 이렇게 되는 거죠. 여기가 이제 부 모멘트 존이고, 여기가 정 모멘트 존이에요. 이렇게 되는 거죠. 그죠? 마찬가지죠. 좀 하나 예를 들어 볼까요? 다 배웠죠? RC1에서? 한번 복습을 해보면, 이게 캔틸레버가 되잖아요. 얘는 철근 배근을 어떻게 해야 되겠죠? 그렇죠? 이거 완전히 모멘트가 전부 다 어떻게, 모멘트 다이어그램은 어떻게 그리죠? 모멘트 다이어그램이 뭐 이렇게 되겠죠, 그죠? 전부 부모멘트죠. 그렇죠? 즉 상부에 인장이 걸리는 그런 상황이죠. 얘는. 그러니까 철근은 전부 위로만 가야 되겠죠. 그래서 이런 것들은 이제 절대 혼동하시면 안 됩니다. Okay, let's design the slabs you see over there. We have to design slabs in two ways because the slab is considered to be two-way structure. Two-way structure, you mean by that is to have a two length which are similar. That's the definition of two-way slabs. Actually, the ratio is greater than 2. In other words, two sides of the slabs are similar. Then you need to design the bars in two ways. You have to design the bar this way, you have to place your rebar this way, and then you have to place the bar this way. So you have a rebar both in x-axis, in y-axis, in two-way slabs. And we need to separate it, as I explained in earlier lecture, we need to separate it, the slab into column strip and middle strip in between. Why? Because the moment in column strip will be greater than the moments in middle strip because the column strip is attached to columns right here. Same here with the other directions. This is column strip and this is middle strips. So that you have to discriminate moment diagrams for each strips. Then how can we determine the column strip width and mid strip width? It is as simple, but it is very confusing for the first time. So listen carefully. Okay. So you need to calculate the L minimum. So what do you mean by L minimum? Here we have two sides for slabs, but they can be same or square slab, or they can be different for rectangular slabs. Do you follow me? If they are different, we call the bigger length L max. We call small length L minimum. L maximum, L minimum. Same here. So this is L maximum, L minimum. So this is a rectangular slabs. So that we use a minimum length, not maximum length. So we use a minimum length and divide that 4 here. So 4 here, divide 4 here, will cover the column strip. Okay. So this is column strip and this is column strip, and in between, of course, considered as a middle strip. It's easy to determine the strip width as long as you remember L minimum. Okay, same here. it doesn't really matter whether you use this when you consider this direction, when you use this when you consider this direction. No. In both directions, you can use same number, which is L minimum over 4, because again you need to use a L minimum. Okay, some students may get confused. They use a this length when they calculate width in this direction, so they divide this length by 4 to get column width, which is wrong. Okay, the direction doesn't matter as long as you got calculate the L minimum. The L minimum is to be used to determine the width of the column strip and middle strip. Do you follow me? Now the difficult stuff will just begin from now on, so please pay very close attention on this lecture from now on. We need to separate it, or we need to divide moment therefore between column and middle strips. Column and middle strips right there, because we have a column strips and middle strips. The reason we are doing this because we need to calculate and add more moment on column strip, because the column strip is attached to columns, so that column strip will take more moment than the middle strip. So this is the concept behind that we divide the strip into column strip and middle strip. So we have a method how to divide and assign bigger moment to column strip. Here we go. Let's take a look at your having a square slab. L1, L2 are same, and this is not square, this is rectangular, but this is square. When you have square, then this number represents the column strips, moment for column strips. Okay, so you need to understand this table very well. This is moment that taken by column strip. The proportion taken by column strips. Okay, the moment percentage taken by column strips. So that when you have a square slab, the column strip takes 75%. That's almost this, right? 75%, 3/4. This is great moment, and we try to design safe for the column strip which is attached to columns. And if we have this and this is rectangular slabs, and you will take 75 same by column strips. So all the numbers are same for column strips, regardless of your aspect ratio of the slab. What's the aspect ratio? Aspect ratio is B over A ratio when you have a B and A. Okay, this is aspect ratio. So it doesn't really matter what kind of aspect ratio your slab has, just the column strip will take 75% of the total moment. Then therefore your middle strip then automatically takes 25% here, 25 here, 25 here. Do you follow me? And what's alpha here? So alpha is a relative, the ratio, the beam to slab stiffness ratio. Okay, so when you have this is a slab, and when you have a beam, the beam is parallel to strip under consideration. So your beam goes this, right? Goes this. A beam here. So that beam has a stiffness. So this ratio is beam to slab stiffness. Okay. So if there's no beam, then alpha is 0. Okay, so calculation can be very easy. So when you have a beam, that you calculate this first and then you pick the number. So when you have a beam, look at here, when you have a beam, as I say here, parallel to strip under considerations, when you have a beam, then column strip will take more percentages of the moment. This is almost 90%, right? And this is less. So this ratio, when you have square slab, don't change, but you take 90% when you have 0.5 aspect ratio, whereas you have a 45 reduced when you have a 2.0 aspect ratio. And in between this, if your aspect ratio is 0.7 something, then you need to use linear interpolations to get value between right here. This is what that means. But this table is applied to calculate interior negative factor of the moment. So this is another important thing. So which means that you want to divide your moment here. Interior negative means at this division you use that table to divide your moment into column strip and the middle strip at interior negative moment right here. It is interior, 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 right? So what about the positive reasons? You have another tables for that. Here you go. We have another tables for the positive factor of the moment. Positive factor of the moment. And also this number is the number that the column strip will take from the moment mu. So this is a square column. Aspect ratio changes makes the rectangular slabs, square slabs, rectangular slabs, and your column strip will take 60 all for 3 cases where you don't have any beam underneath the slab, whereas when you have slab, your column will take more or less, and same as for interior negative factor at the moment. So this divisions represents this part right here, positive moment, positive moment. So now using 2 tables, we're ready to divide the moment into the column strip indicated by red and the blue representing a mid strip moment for mid span and interior negative. And it is pretty simple as you understand the table well, otherwise could be confused. So practice yourself sometime. So the following example again from the Professor 김상식. 지금부터 나오는 예제는 또 철근콘크리트 구조설계 4판 김상식 교수님께서 쓰신 문운당에서 나온 책을 참고로 합니다. 감사드립니다. So let's calculate a moment. We need to calculate moment this way and this way so that we can design. Without moment we cannot design, can we? So we have moment here, some moment this way, and we have moment this way. Understand? Okay. So this moments calculated and then divided by into column strip, middle strip. This is the first way to design slabs. First of all, we need to assume a slab thickness. Slab thickness can be assumed using this table when you don't have a interior beams. And this example, we don't have any beams interior. We have exterior edge beams, but we don't have any interior beams. Then we can use this table to assume thickness of the slab. This is very convenient table. And when you do this, we need to calculate the span lengths inside of columns. So we need to span lengths inside of columns from here to here. Okay, here. This is what we need, right? So this is 6 meter, and we have a column size 400. So the span inside the column will be 5,600 millimeter, which is pretty easy. So when you use this table, so we call this GPAN, column capital. Then I will explain how to design column capital in future lecture. And you need a column capital to prevent a punching shear. And we'll take a look at that later. Punching shear here, which protect the slab from failing due to the punching shear. So when we don't have a column capital for this slab, so we go into this side and we pick this value for 400 Fy, because 400 Fy is given here. So this table is very convenient. We choose ln over 33, which is 170. We take 180 as a initial thickness of the slab. See, initial thickness of the slab. Okay, so we verify this later. And then we have a cover 20 millimeter for slabs. The cover is this slabs, and this is the rebars here, and this is cover, isn't it? So this is what we learned from RC1. Okay, so this is the effective depth of the slab. This calculated, you're subtracting cover and you're subtracting half of diameter, which is radius of the rebars, from 180, which you assumed as a initial thickness of the slab. So you got this right there. You get a 150 millimeter. And we have now every information to calculate the statical moment. What's this statical moment? Statical moment is this, as we saw in previous lecture, and we have a omega L squared times the width of the slabs right there. So ln is a clear length, and we calculate 5.6, and 5.4 is another the width of the slabs from here to here. This is the width. This is the width L2, and this is ln. So if you remember, we get this formula for calculation of statical moment, total statical moment, and 12.1 as a load intensity is given right here. It's given right here. So don't miss these units, kilonewton per area. So we calculate this. This is a total statical moment. Total statical moment is everything. Total statical moment. So we need to divide this using a moment diagram, also we need to divide this into column strip and middle strip. We have a long way to go. First of all, we want to calculate the bending moment diagram. Something like this that we see previous lecture, right? So then we need to know the boundary conditions, right? First, then you can go into the table and pick up the number as we saw. Our boundary condition is that we have a edge beam and we don't have any interior beams. So I summarize right there with the edge beam and without interior beams. And what's the number that we can pick up from the table? We can pick up this number from the table. Let me go there. Okay, if you see over here, see this one, isn't it? I'm looking for this one. See, without any beams, and then we have a edge beam. So we pick up this is exterior span, exterior 0.357 and mid 0.5 and interior is 0.7. So we are having these diagrams. Everybody follow? Now this is very convenient, as I said. So we have a interior span, negative moment here 0.65 and positive moment here 0.35 is all repeated, right? All interior moment has same coefficients as I said, except the last span. And we have here 65 and 35, 65. And we have a total statical moment. It's going to be substituted in here. And this is why we call this total. So we have to divide into to calculate bending moment diagram depending on the boundary conditions. Also the exterior span is exterior mid interior. So this is 0.3, 0.5, 0.7. So we also substitute it here. Okay, so we got this moments here. So now we can write numbers here. Here we got numbers here. So we got here 0.3, 0.5, 0.7 and 65, all that, right? And we have numbers here. But these numbers, this moment is 0.3 m0 is 76.8, 0.5 m0 is 128.1, and 0.7 m0 is 179.3, and here 65 coefficients will give you 166.5, and 35 coefficient will give you 89.6. Okay, because your statical moment is this. Now you're not done yet. We have to separate this moment into, yes, column strip and middle strip. That's the last task before we design. We need to use this table to calculate the moment taken by the column strip, and we have a square slabs. Why square slab? We see this here 5.4 this way and 5.4 this way. So this is 5.4 this way, and we have 5.4 this way. So we assume that this is a square column, which is a aspect ratio of 1. So we can just use this. This is the case where we're going to pick the number for column strip that takes from total statical moment, and that's the how many percent is that? This is a this one. How many percent is that for negative? Interior negative, you'll take 75 by column strip and 25 by middle strip. Whereas we have here a positive factored moment. We have a 60 by the column strip and 40 by the middle strip, and that's the positive factored moment when you have a square slab with the aspect ratio 1. So if you go here, see this diagram summarizes what you've seen so far. So mid strip, this is mid strip, isn't it? And of course we don't have any alpha, because alpha is 0, because we don't have any interior beams. So it makes your life calculation very easier. But if you have a alpha, you need to consider, this table, which is not a big deal anyway. So 60%, 40% for positive, and 75 by 75 by 25 by the negative interior. So this is the moment portion taken by the column strip. This is moment portion taken by the middle strip. And you're multiplying statical moment here again with the based on the bending moment diagram you just obtained, right? So let's go back to summary table right here. So now here, this is your bending moment diagram, and you have to divide that by 75 to 25, right? 75, 25, isn't it? See, let me double check. $75, $25, right? Okay, and then positive 60, 40. Very comfortable. Do you feel comfortable? See, this is 75, 25, and this is a I'm sorry, we don't get that yet. Let's talk about this later. This is a different story. Okay, so we just talk about the interior here and the positive here, all same. So this is a total statical moment based on a bending moment diagram, and this 75, 25. I'm sorry, 60, 40, right? 60, 40. And this is also 60, 40 based on this moment, and 60, 40 based on this moment, right? And then here 75, 25 based on this moment. 75%, 25%. Of course, 75% by the column strip, 25% by the middle strip for this moment. So we got all the moment for designing slab except the exterior span of exterior end, right? Why this is not done yet? Why we cannot apply this formula here? Why not? Why we cannot apply this? But if you have a H-beam like that, then you have a separate table to calculate and divide that into column strip and middle strip. Let's take a look at that. When you have a H-beams here, let's take a look at division between column and middle strip, exterior negative factor moment when you have a H-beam. So the H-beams will allow you to use a different percentages, so that if you have a square column and with different aspect ratio, when beta equals 0, then you can just take everything by what? Column strip. Which means that if you don't have H-beam, the edge moment, entire edge moment is taken by the column strip, so that you don't need to design middle strip. Do you understand this number? Do you understand this number? This number. When you have a beta which is greater than 2.5, you have 75 as before. In between here, between 0 and 2.5, you interpolate. Okay. And this is for when you don't have any interior beams. So in this particular example, we don't have any interior beams. So alpha 1 equals 0. So you can follow this formula. Okay. But we need to calculate beta. I didn't explain how to calculate beta yet, but I'll explain right now. When you have a interior beam where alpha 1 exists, then you can go and calculate beta again, and you follow the ratio similar to this one except 90, 75, 45. Okay, so this means that we want to design conservatively. Okay, we want to design conservatively. At H, we want all the moment is taken by the column strip. This is H. The H will take a column strip to take all the moment here. This moment is taken by the column strip only. This is the way that we want to have a conservative designs, right? So calculate how to calculate the beta. Beta is calculated based on this formula. This is based on a torsional rigidity that we learned from mechanics of materials, and where we calculate C based on these dimensions. X and Y is the dimensions that I'm going to show you right now here. See, this is how you calculate the C and beta. When you have a H beam here, so first of all we need to calculate the torsional rigidity of this edge. How this edge, of course this edge is perpendicular directions to the strip we design. We design strip this way, or bending moment this way, then wedge H beam go this way. Right? So this is perpendicular to the strip under considerations. Okay, so if you see here, so we're gonna skip the derivation of the torsional rigidity, but I'll explain directly how to calculate the torsional rigidity, torsional stiffness due to the H beam directly. If you see over there, first of all, you need to divide the H beam and slab in this ways. One, there's two cases where you can model your H beams. So first of all, you have H beam, something like this, including your slab portions. And second case, your H beam do not include slab portion. Okay, so first of all, you have two types of H beam configurations. Okay, configurations. And then we assign a long dimension by Y. This is Y, and this is Y. So of course this is X, right? And this is X, right? And here in this case, and this is long side for this rectangular. So this is Y, and this is X, and this is long side of this rectangular, right? So this is Y, and this is X. So now we use a formula that's given before here. This formula, and we substitute X and Y accordingly. I said the long long dimension is y, short dimension is x, and long dimension is y, short dimension is x. And we have the first configurations with this 5,389 times 10 to the 6 millimeter fourth. Right? We have similar calculation this here. And between two, we choose big one. This one. So we choose this, and I, which is moment of inertia, is easy. BH cube over 12. This is the moment of inertia that we learned from previous classes. And this. Now we're ready to go and plug all these numbers in here. We have a C, we have a IS, we get this number 1.03. So that as long as we have this condition where we don't have any interior beams, so this goes to 0 and we get 1.03. So we have to go and get the number from this table. But you know that we're gonna select this part, but we have a 1.03 beta, right? So we need to interpolate these numbers in between somewhere here. This is interpolations. Okay, this is not that difficult. So we get number which is 89.7 by the interpolations, so that the column strip here in this particular area, the column strip will take 89.7% of total statical moment. So now do you follow? So that here this is total statical moment, and this total statical moment is divided into the column strip and middle strip depending on the ratio, which is what? I forgot. 89.7. 89.7, almost 90% and 10%, right? So yeah, this is 10% of this, right? Okay, so we have now separated all the statical moment based on the bending moment diagram into the column strip and middle strip. So as you see over there, the column strip moments are greater than the middle strips. Why? Why? Yes, column strips are attached to the column directly, so that it naturally takes more moments, which means that we have to design column strip more strongly than the middle strip for safe slabs. Okay, this is very important. Okay, this is very important, and this is summarized. Okay, so now we will make a table that represent this. Okay, we can just use this as design. For example, you can design levers for this moment for column strip at exterior. So now, are you familiar with reading these tables? So this is a moment for column strip and middle strip for exterior span positive moment. Yes, and this is right here. It's summary of the bending moment diagram. This one. And, actually, I prefer taking a look at this when I design, because this is somehow confusing. But it doesn't matter. You can use this for design and use this for design. All right. And finally, we got this, and we will try to wrap up this example in next lecture. So I try to slow down this lecture as possible for you to understand and follow me. But even though you don't, some of them I'm sure you don't, but you can repeat this video as many times you want repeatedly and make a good note. And this concept is very important. You just study the concept as to how to design two-way slabs today. If you understand the concept today, then all the rest of the lecture for designing two-way slabs are very similar. Very similar. You will enjoy the rest of the slab design, and even if a little bit complicated, because I want to show you some of the real hot slab design example, and I made a very significant effort on making note. So, but before we get into their topic, you need to review today's lecture thoroughly. Thank you.